Today, let's look at the system design for consistent hashing. To achieve horizontal scaling, it is important to distribute requests and data efficiently and evenly across servers. Consistent hashing is a commonly used technique to achieve this goal. If you have n cache servers, a common way to balance the load is to use the following hash methods. You'll have a server index, you'll take a hash key mod n, where n is the size of the server pool. This approach works well when the size of the server pool is fixed and the data distribution is even. However, problems arise when new servers are added or existing servers are removed. Consistent hashing is an effective technique to mitigate this problem. Quoted from Wikipedia, consistent hashing is a special kind of hashing such that when a hash table is resized and consistent hashing is used, only k by n keys needs to be remapped on average, where k is the number of keys and n is the number of slots. In contrast, in most traditional hash tables, a change in the number of array slots causes nearly all keys to be remapped. So hash space and hash ring. Now that we understand the definition of consistent hashing, let us find out how it works. Assume SHA-1 is used for the hash function f, and output range of the hash function is x0, x1 till xn. In cryptography, SHA-1 hash space goes from 0 to 2 to the power of 160 minus 1. That means x0 corresponds to 0, xn corresponds to 2 to the power of 60 minus 1. And all other hash values fall in the middle between 0 and 2 to the power of 60 minus 1. Using the same hash function f, we map servers based on the same IP or name into the ring. Cache keys key0, k1, key2, and key3 are hashed into the hash ring as seen in this diagram. To determine which server a key is stored on, we go clockwise from the key position on the ring until a server is found. Going clockwise, key0 is stored on server 0, key1 is stored on server 1, key2 is stored on server 2, and key3 is stored on server 3. Now, adding a server. Using a logic described above, adding a new server will only require redistribution of a fraction of keys. In figure, after new server 4 is added, only key0 needs to be redistributed. Key1, k1, key2, k3 remain on the same servers. Let us take a closer look at the logic. Before server 4 is added, key0 is stored on server 0. Now key0 will be stored on server 4 because server 4 is the first server it encounters by going in the clockwise direction from key0 position on the ring. The other keys are not redistributed based on the consistent hashing algorithm. When a server is removed, only a small fraction of keys require redistribution with consistent hashing. In figure presented here, when server 1 is removed, look at the server 1, okay, it's removed, only key 1 must be remapped to server 2. The rest of the keys are unaffected. Two issues in the basic approach. The consistent hashing algorithm was introduced by Garger et al. At MIT. The basic steps are map servers and keys onto the ring using a uniformly distributed hash functions. To find out which server a key is mapped to, go clockwise from the key position until the first server on the ring is found. The problems identified in this approach are: first, it is impossible to keep the same size of the partition on the ring for all servers considering a server to be added or removed. A partition is the hash space between the adjacent servers. It is possible that the size of the partition on the ring assigned to each server is very small or fairly large. In the figure shown here, if S1 is removed, S2's partition is twice as large, highlighted with the bidirectional arrows, is twice as large as S0 and S3's partition. So there is a partition scale. Second, it is possible to have a non-uniform key distribution on the ring. For instance, if servers are mapped to the positions listed in the figure, most of the keys are stored on server 2. However, server 1 and server 3 have no data. A technique called virtual nodes or replicas is used to solve this problem. So what's a virtual node? A virtual node refers to the real node, and each server is represented by multiple virtual nodes on the ring. In figure, both server 0 and server 1 have 3 virtual nodes. The 3 is arbitrarily chosen. In real words, the number of virtual nodes is much larger. Instead of using S0, we have S00, S01, S02 to represent server 0 on the ring. Similarly, we have S10, S11, S12 represents server 1 on the ring. With virtual nodes, each server is responsible for multiple partitions. Partitions with label S0 are managed by server 0. On the other hand, partitions with label S1 are managed by server 1. As the number of virtual nodes increases, the distribution of keys become more balanced. This is because the standard deviation gets smaller with more virtual nodes, leading to more balanced data distribution. Standard deviation measures how data is spread out. The outcome of an experiment carried out by Outline Research shows that with 1 or 200 virtual nodes, the standard deviation is between 5%, that is 200 virtual nodes, and 10%, 100 virtual nodes of the mean. The standard deviation will be smaller when we increase the number of virtual nodes. However, more spaces are needed to store data about virtual nodes. This is a trade-off, and we can tune the number of virtual nodes to fit our system requirements. So here's the summary. The benefits of consistent hashing include minimized keys are redistributed when servers are added or removed. It is easy to scale horizontally because the data are more evenly distributed. It can mitigate hotspots key problem. Excessive access to a specific shard could cause server overload. Imagine data for Katy Perry, Justin Bieber, or Lady Gaga all end up on the same shard. Consistent hashing helps to mitigate the problem by distributing the data more evenly. Consistent hashing is widely used in real-world systems, including some notable ones. Partitioning component of Amazon's Dynamo database, data partitioning across clusters in Apache Cassandra, Discord chat application, Akamai content delivery network, and maglev network load balancer. Hope this content was useful. Have a nice time. Like and subscribe for more such content.